Welcome everyone to Amplify Marking Matters. We have 2 interesting hours ahead of us, whether you're joining live or on replay. I'm Alexander Ruff, Vice President and General Manager of Coherent Industrial Systems, and I will be your host during this event. Laser marking technology has been widely adopted throughout many industries, whether it's semiconductor manufacturing, the automotive industry, consumer goods, or medical device manufacturing. But actually, today it goes way beyond high quality and flexibility. Marking technology ensures the seamless integration of today's manufacturing data streams into an Industry 4.0 environment. And that brings us to today's theme, laser marking from concept to production, application, verification, traceability, quality control, and connectivity. Coherent has been on the forefront of laser marking technology for more than 3 decades, and we continue to innovate to meet customer requirements and industry demand. You will hear today from Coherent experts and guest speakers interesting insights and have a peek into our application lab and see our latest technology advances. We will have a Q&A session towards the end of the event, and you can post your questions into the chat box. We will answer as many as we can, time permitting, during the event or get back to you right after. Also expect me to drop in throughout the event as your host. Finally, let me thank our customers and loyal partners for continued business and support. So now let's get started with the agenda and the first topic, which is application, vision, and verification. And we start where everything starts, in the application lab, where we develop laser marking processes for the production requirements. Our first speaker will be Thorsten Ferbach. Thorsten is our product line manager for marking systems. So over to you, Thorsten.
Thank you, Alexander, and hello to everybody. So as already mentioned, application, vision, and verification are 3 very important subjects for us in order to discover new fields of innovation and to drive benefits for our customers. If we look into the laser marking ecosystem, basically laser marking in terms of applicability for track and traceability, quality marks, functional marks, is meanwhile a standard in modern fabrications. So we see here a production line with a laser marking cell integrated, and this stands for one broad bandwidth of various laser technologies, fiber lasers, diaphragm solid state lasers, all kinds of wavelengths. So this is in this ecosystem meanwhile state of the art, accepted and widely spread into the various industries, from the medical device industry, consumer electronics, automotive, packaging industry. So where we have potentials to drive innovations. Let us look first into the subject of application. Application, of course, has something to do with the laser source itself. The technology platform, so what it is, it's a fiber laser, it's a diaphragm solid state laser. If it's a green, infrared, or ultraviolet laser, or what kind of beam profiles we are using. So all this has a kind of benefit in terms of throughput and quality of the marks. The other area is the subject of vision. Subject of vision becomes more and more important. It has a responsible role before marking in order to position parts, and has as well a responsible role after marking when vision takes over the verification and inspection of the mark. This can be reading a datamatics code or any other industrial codes, but it can be also a kind of contour check in order to provide data for verification. Verification is basically the last area. So it's about connectivity. So all the information about laser process data And production data can be collected in our ecosystem for laser marking and can be, by connectivity via interfaces, deployed to various information systems in order to execute this information and improve our performances. So let's start to look into the details. Let's look into the first subject, application, and let's focus on the increased performance. I have purposely selected you two examples, our twin laser technology and the UV laser technology, which make a difference in order to increase your throughput, in order to make your manufacturing faster and more efficient. What is twin? Twin is basically the cooperation or the collaboration of two single laser marking heads controlled by a single supply unit and a single marking file. It's a simultaneously asynchronous marking. So we can think about large-scale parts, matrices, etc. So in both cases, we can achieve a faster throughput. The two units are controlled with a single device computer with a single VLM file, which is our marking software, which is our marking file format. And the two heads decide by themselves how they cooperate in order to come to a fast and performing marking result. The other subject I would like to highlight is our high-power UV laser technology. Coherent stands for strong UV experience over a long-term period. And UV laser technology, of course, it's commonly known in various industries, but we deploy it more and more into the packaging industry. As packaging is a high speed and performance marking, basically, we also have to deploy highest output power levels. So that means we go beyond the usual levels of UV output power level and use this for fast and efficient marking and packaging industry, medical consumers, etc., where usually marking requires UV laser for the marking result on the plastic material, for example, but in the same time to really leverage the performance in terms of parts marked per minute. The other area I would like to highlight in the field of applications is the improved material processing. So today, functional materials or very delicate materials require a much more careful processing with a laser. So here I want to highlight our Smart Protect technology and the utilization of ultra-short pulse lasers for marking applications. What is Smart Protect? Smart Protect is basically a harmonized beam profile. When we look for a diode pump solid state laser with this Gaussian beam profile, we know there's an energy cluster in the center with a higher energy impact on the material. This is sometimes not ideal for the material, especially when it comes to sandwich materials with very, very thin layers, where there is a potential to damage with a laser marking the layer below. So therefore, it is usually often used for shallow depth marking, so something very, very shallow at the surface. And in addition, it provides as well faster marking because we can use the entire diameter of the beam in order to apply the same energy density. Ultra short pulse lasers is another very famous example of our innovation creation. Innovation creation here by the long-term history and experience of us active in the field of picosecond and active in the field of femtosecond lasers, utilizing these laser technology platforms in standard marking solutions and gaining ahead of the usual material properties advantages like corrosion resistance or certain functional surface properties like hydrophotic stuff. So what does the femtosecond or picosecond laser make different? There's less energy impact, so there's less thermal stress. So that means in the same time, it also offers the opportunity to mark very fragile parts. So let us move on into the vision subject. And let's have a look what vision can provide you before marking takes place. And this is, of course, the high accuracy. Today, basically, operators would like to have an easy and convenient and simple setup of a job, a marking job with a vision routine included. So this starts already with the avoidance of fixtures. Fixtures are costly. They need mechanical preparation. If that's possible to avoid with a vision system, it's ideal for the customer. Second, the customer has to tune the file, program the vision routine, and has to have support by the software behind. Our laser framework with our vision routines, our preset and predetermined vision routines, basically offers AI supported, so means computer aided help to the operators to file the individual vision job in order to program a 2-point correction for X, Y, and angle offset correction. These vision systems are containing a vision cube. It's an optical element between the laser source and the scan head, a camera which looks via the scan head on the part on the same axis like the laser axis, and of course an illumination. On the right-hand side, we see a part which is placed without a fixture and where we do a contour check. Basically, with this contour check or real workpiece check, basically the entire tray or a single part can be detected if it's the right one, if the contour is right aligned, as well as what is the offset in X, Y, and angle correction. So it's a simplified production process. And later on, we will see how laser framework and the setup of such a vision job looks in reality during our lab day. Mark inspection, utilizing the same kind of vision technology after the mark, helps for post-inspection of, for example, industrial codes. This can be a data matrix code or UDI according to GS1, a QR code, barcode. But that's not all. Basically, we can also look into industrial font types, OCR, OCV font types. We can check for contours. We can do topology recognition. And this all supported with a very simple and easy interface in order to program and deploy this information to other systems. So what's about verification? Verification means, first of all, gaining the information, collecting the information, and sending it somewhere in order to execute this. So that means this data lodging is basically depending on the interfaces. So there are various industry interfaces widely spread. So we have MQTT, SexGem in the semiconductor industry, Fieldbus, OPC UA servers, etc. And all this together collecting the information from the process, whether it's the laser parameter or the process parameters. Both is basically important to know for quality assurance, for documentation purpose, or any other further topics what is interesting for the customer in his documentation of his part manufacturing over the process and the lifetime. So how we put this together? And here I would like to present you our new release, our versatile marking machine, the Exact Mark 210. This is a complete solution. This conclusion features all the subjects before I have mentioned before. So we have all the possibility to integrate all power line laser markers in the wavelengths 1064, 532, and 355 nanometers. We have X system for part positioning and part movement. We can use different kind of field size, beam shaping opportunities. We can do 3D marking by a fast focus shifter, etc. We have vision system for pre and post inspection. So that means we can proceed fixtureless marking. And of course, we have interfaces for part fixtures and clamping. All this supported by Laser Framework, our new HMI, our new GUI, which my colleague Daniel will now show you in the now following lab demo. So please hand over to Daniel and have fun.
Hi, I'm Daniel Seitz, Manager Innovation and Application at Coherent. I'm guiding you through the lab demos today. In both lab demos, we're going to use the Exact Mark 210, the latest member of the Exact family. The Exact Mark 210 offers powerful internal and external interfaces up to 2 axes and can be equipped with various marking lasers. The one over here is equipped with a diode pumped solid state laser and a vision system that consists of a through the lens camera and an 8-segment ring light. In the demo now, I'm going to show you how to mark this demo part with our latest HMI, the laser framework, and vision positioning. It offers easy setup and accurate positioning. Let's dive into the software. First of all, I insert the part into the machine and continue setting up a new recipe. At first, I define the sequence of process steps needed for the demo part. The vision process, the drawing execution process step, and later on, the reading back of the data matrix code. I already prepared the marking file, so we can save some time here. As you can see, it consists of the contour of the workpiece, the Amplify logo, and the data matrix code. Let's go back to the vision process. The easy-to-use Smart View feature helps you pre-aligning the drawing content. Clicking on the part and selecting the hand, you can, with 4 simple mouse clicks, pre-align the layout before continuing with the 2-point search process. The easy-to-use wizard on the right side guides you through all relevant process steps needed to set up the process. Live view, axis position, region of interest, the teach mode, and at the end, the test mode. I'm going to demonstrate this to you by starting the test and moving the part while the test is running. As you can see, the vision system still detects the part correctly no matter where it is. After setting up the second search point, we are ready to execute the already existing 2 process steps. After successfully setting up the positioning of the part, we continue adding the 2D code verification to the recipe. We add another process step and drop the 2D verification on top of the metrics code, and similar to the positioning, the step-by-step wizard guides you through all relevant steps to define the verification process. Now the process is set up completely, and we continue by adding a new part to the machine. I then start and execute the complete process again. This was our first lab demo. Now over to Dave Girardot, who will talk about automated part handling for laser marking.
Good day, everybody. I'm Dave Girardot from the Plymouth, Michigan facility. Today I'll be talking about marking system automation specific to part handling. So let's begin here. So automation, typically when we talk to customers and prospects, there's always a problem to solve. And usually the problem or problems to solve are related to customers wanting to squeeze more products through their systems. And of course, everybody wants to go faster. And lastly, but not least, with improved or better quality. So let's talk about some of these categories of automation to achieve those wants and desires. So specific to the machine system level of automation, there's a couple different categories. One is programmable, much like a robot or other device that gives you some flexibility to move parts, place parts, inspect parts, that type of thing. It really gives you the most vast array of freedom when it comes to automation. Next is flexible. Flexible gives you some discrete types of flexibility to adapt to different part types among a family, things of that nature, with some limitations. And fixed, as it says, it's fixed. It really doesn't give you any adjustability or versatility. It's all fixed as is. And then finally, the last category is combined. So combined gives you one or more of the various categories described above combined into one, where you might have some programmable aspect or flexible or fixed aspect within that that cell or machine or system or line. So next up here, this graph I'm displaying kind of gives you the relationship between these various categories and their volumes. So for example, on the fixed type category, you typically have much higher volumes versus the programmable automation. You have lower volumes and typically a higher part mix. So let's look at a couple examples of this. So this here we have a conveyor line. And it's conveying transmissions. And this is a sample of the fixed version. So there's 3 different transmission styles that the customer would convey, but from the outside, they're all identical. There's some differences inside. So what we're doing in this case is we're actually reading an RFID tag that's located in that white fixture plate at the front that's sitting on the orange conveyor material. So as the part transmission is indexed in, we read the RFID tag in that white fixture that tells us all the relevant information and what to mark. When we're done marking, we write to that RFID tag, and that lets the internal systems know that we've done the marking job for that particular part, and then it's indexed to the next part. So some things to look for here, key considerations is the part fixturing precision needed. So when you have a part indexed in, you have all these tolerances you're dealing with, from the part to the fixture to the conveyor to actually where you're going to mark the information. So those are things to keep in mind, very important. And again, as mentioned in the earlier graph, this really deals with higher type volumes. And again, it's inflexible. So at the bottom of the page here, I have this blue rectangle, and this represents the marking real estate. And of course, like anything else, you want it to look nice. You want the marking information you're putting in there centered and all these things. But when you add up some of these tolerances, sometimes you don't get a nice centered mark. The ABC 1, 2, 3 can be off to the side or tilted at an angle, much like I'm showing now. So keep this in mind when you're thinking about conveyance systems and what the needs are from marking this information and the requirements to get that mark in a particular location. So let's move on to our next sample. The next sample here is flexible. So the flexible hard tooling, as I call it here, what's pictured here is one of our marking systems. This is a rotary dial index table. So this round disc here pivots 180 with the parts fixtured on top of these fingers here. If you can see these stainless steel fingers poking up. Now this tooling is interchangeable. So there's a 5 or 6 different product families that fit within this tooling, different lengths, different diameters, and so forth. So this allows us to change this tooling to accommodate the parts. And then also in changing the tooling, we can change the laser recipes and other facets of the system specific for that particular part style of that part family. So this is what we call flexible. And of course, on the operator side, to ensure that you have the right fixture and the right recipe and so forth, there's some checks and balances on the machine that allow the machine to verify that everything's been changed that needs to be changed. So poka-yoking, those types of things are often required on this type of a setup. So that's flexible automation. So some additional considerations. Typically, you're limited to 2D part processing versus 2 or 3D part processing. Again, dedicated part or part families, as I mentioned. Medium volumes. All right, moving on to the next, programmable. So this is typically where we have robotics and other programmable devices. What's pictured here is a assembly line, and these robots are picking and placing components onto a PCB board, and then downstream from this picture we actually use vision along with the marker to mark various aspects of the product. In this case, they're picking a very small part, placing it again on the PCB as an assembly process. So some of the considerations for this, of course, is your load capacity. You can have much larger parts to pick and place, which you have to be concerned about your load capacity, especially at speed. Small parts are easy. As the part mass increases, you have to be careful you have your robot sized properly, and you're not losing grip of the part during the actual transfer process. Additionally, articulation needs. The advantage of the robot here, obviously, you can articulate the part in an orientation that might be more difficult to do with other means. So 2 or 3D articulation of the part to get it in the right location for assembly or marking processes. Typically with this type of setup, you also have what's known as batch production, lower volume. So you might run hundreds or thousands of parts and then switch to a different part or product type. And again, run hundreds or thousands of that and then back and forth. So not the high volume like the fixed category. Additionally, not only this category, but other categories, you might run into industry-specific standards that you have to accommodate. For example, semiconductor has their own standards. You may have to apply this in a clean room application, things of that nature you have to be aware of, and when selecting your automation and the environment in which it's used as well. Okay. So moving on to one of the last categories here is combined. So combined, as I mentioned earlier, combines one or more of these different categories. What we have pictured here is within one of our marking machines, we actually have a camera inside looking down onto the actual machine. And you can see there is a yellow robot, excuse me, a yellow robot, the gripper. And at the top of the page, we have an input bulk part feeder. We're processing tubes, and we advance one tube at a time for the robot to pick up from the top of the page. On the left-hand side of the page is our good part drop-off, and then there's a stainless steel area that's actually a bad part bin where we drop off bad parts if we make bad parts, which usually we do not. So. And then off to the right of the machine, there's a silver box, that's the actual galva where the laser beam's coming out of. And then we have a rotary collet that actually accepts the tube and spins the tube and places it as we mark it. So some considerations, again, it's combined, so it's more of a lower part volume aspect with multiple parts and parts families. As I mentioned, we're processing tubes here, so the tubes can come in lengths of up to about, I think 20 inches down to about 3 or 4 inches, and small diameters from 10, 15 thousandths in diameter to about 6 millimeters in diameter. Again, medium type volumes as mentioned. Just recapping here, it's an automatic input robot, and then there's a vision and some sensors looking at the end of the tube so we know where to start marking, as well as examining some of the mark information via inspection. So, and here's a picture of the actual part. So there's some dark bands, some numbers, and some other information that we place on there, and then verify we've actually performed the mark. So let me click on this and see if we can get the video going. So you'll see some little blurbs of light there. The robot grabs the actual marked part, puts it in the good part bin, grabs the next part, puts it in the rotary chuck. The vision flash of light finds the end, and then as we're marking, we're actually able to look and see the actual bands we're producing, and then the process repeats. So it's going rather quickly. This is at actual speed. This is not sped up or slowed down. So again, the light flashes and begins the process, doing some marks you can see there. And onto the good part bin and grab the next part. So the the part bins, both in and out, are what we call flexible tooling. We can accommodate different part lengths through moving some part tools around and some other adjustments. The collet in which we're putting the tube and rotating for the marking. The collet has a range of tube sizes or diameters it can receive. And then there's a variety of collets that can be replaced for different tube sizes. So that's also flexible. And then the robot and the vision are the programmable aspects of the automation. So, okay, so let's move on to the next slide here. So some other considerations and influences when we're selecting our automation from the manufacturing environment and the system control and data acquisition, what I call our facility hierarchy. So every equipment data exchange with the systems and equipment control and production processes. And so you have to make sure that this equipment that you're implementing will mesh with all these different systems, so they mesh and work well together. So it often takes considerable effort, time, and coordination to make sure all these come together and work well. So please keep this in mind when selecting your systems. Other influences from the outside world, I'll call it the Internet of Things, a long time acronym of what's going on with getting everything digital, if you will. Industry 4.0 as well is a big influence on us. Coding, I have a picture of a UID code here at the bottom. Excuse me. This coding for traceability is very common in all different markets, from aerospace, from government to medical. There's all types of traceability going on where you have to, for example, with vision systems, log the actual images you're taking from the vision and keep those for indefinite periods of time for traceability issues. And of course, the coding, so you can track the product through your plants, and also once it gets outside your plants for traceability. And then last but not least, security. So this day and age, as we all know, with all kinds of bad actors hacking our systems and causing havoc for everybody, in which I'm enjoying right now. I live in the Southeast US, and some bad apples have hacked into one of our pipeline control systems. So everybody in my area is running short on gasoline for their vehicles. So I'm living part of this right now, so I can understand the issues it causes. So please be aware of security when you're also thinking of these systems. So last slide I have here, this is just a code, and this code will get you to our YouTube site to see the video I shared in the previous slides on the highly automated system for marking tubes. So thank you for attention. Appreciate your time. Hopefully you found this valuable and learned some things. And next up is Josef talking about some marking and programming aspects of our systems. Thank you very much.
Thank you, Dave, for introducing my presentation. This is Amplify Laser Marking. I'm Josef Pfaffinger, Software Manager at Coherent, and I will talk about integrating the laser process with production. I will open up again with marking, but marking as a function with the most important attributes. Here we see on the left side the reliability over lifetime, because a barcode uniquely identifies each product. So with this, it's possible to retrace the path of any product through the factory. And we like this traceability because in case of a car, if it is our car, we like it when we get the recall. So from each component, there are different variants, like this PLC component on the right side of this picture. And those different variants get the data right from the product mix just in time, and this is the highest flexibility only a laser marker can provide. So for all these functions, it is necessary that the laser marker is integrated into the manufacturing process. And high marking quality of text combined with data communication is one of the key laser requirements, and that is a big step closer to Industry 4.0. And maybe this is actually another generic term for this presentation. So on the next slide, we will talk about how this does fit into a production. The factory on the left side produces almost infinite numbers of PLC components. And each of these gets marked with a unique identification and the corresponding product data. And you can imagine a series of lasers are integrated into this production. And in this extremely high automation and integration, this requires a smart control system. And the control system of such a high automated fab is a MES, a manufacturing execution system, whose definition on the right side is showing the relation to our laser marker. And the laser marker gets the data at the right time, marks, as we have seen it in the previous slide, and sends the product data for quality assurance or traceability back to the fab IT. And we will see more in the next guest presentation, but now we're gonna take a closer look at the software interfaces of a laser marker. What does this mean for a laser marker? On the left side, we see the communication pyramid, which is probably in most fabs the model from shop floor on the bottom side up to the top floor where the enterprise resource planning system is sitting. And the laser marker, laser marker is sitting in the middle at the SCADA level, system control and data acquisition. So here we are sitting with our laser marker or laser framework. And here protocols and data interfaces are realized for vertical communication along this pyramid and also horizontal communication along the production process. Jobs are loaded, data variables will be assigned, remote functions will be called or executed, databases provides the marking data, and production and performance data are uploaded after marking. On the right side, we see a number of industry standards which already have been implemented. And with our laser marking system, it is possible just to configure the appropriate communication for almost every factory interface. For many standard tasks, we already prepared interfaces with our laser framework, like for the semiconductor industry, usually they use a SexGAM interface, automotive using MSMQ, message queues, remote function calls to an ERP system like SAP, ODBC for databases, etc. So these interfaces are connected via a network, which we look closer on the next page. The network, which is connecting the machine from the left side to the customer PLC and the MES, as we have seen it in the communication pyramid, and up to the intranet of the fab, or even up to the cloud. So this is from the machine to the internet to the cloud, end-to-end communication architecture. So with our laser system, the individual control components like the laser, the machine, the PLC are networked and connected to the customer PLC and MES system. Edge device for high data throughput can be installed. Edge means it's at the edge of the machine, close to the machine, and doing the asynchronous data processing, not charging the machine from its real laser process. Networking the laser with the PLC and MES up to the edge and up to the cloud opens future solutions, which we are looking at. And with those solutions, like the service on the right side connected via the cloud to the machine, we will get virtual business models in a digital production environment. And this already became real. So we are in a pilot project where we're connecting an edge device and our laser with an internet router to the cloud. So, as we say, the future has already begun. And besides a highly automated production, we see new use cases on the horizon, which will probably integrate it in the MES landscape or side by side in a special maintenance server, for example, and will open up additional values like predictable maintenance. In this rapidly growing virtual business world, Coherent is working on a OPC-UA connector for laser systems. This is an interface standard which will enable us to implement the necessary use cases, which we see on the left-hand map. And this will open up a connection. We integrate the laser marker into the fab in a plug-and-play manner. And this definitely will save costs on the fab side because we will downgrade the downtime, or we will reduce the downtime. And on the vendor side, on our side, we can save travel costs for the service and spend the service guys remotely connect to the interfaces to the laser and maintenance the laser by remote. So we will continue to learn and develop laser processes. We will collect data together with our customers and we will and partners, and we will drive further solutions to improve and continue to provide best-in-class connectivity of the laser marker. So this was a fast journey from laser marking over the MES system to the cloud. And I thank you very much. Enjoy the next presentation. And now I'm giving back to Alexander. Thank you.